Hello, everyone. Today I want to talk about the exponential form and how we use it and some things about it. And it's really, in my opinion, review, because you probably had this in analog circuits or someplace else. But I always like to go over it when I start talking about field theory, because we'll use it sometimes and it's so good to understand, and it's the only form that electrical engineers going forward are going to use in any type of things like antenna design or phased array radar, or this is the only form you're really ever going to use, because it encapsulates the whole thing and everything, and it makes the math so much easier, because the math you're going to use isn't just going to be arithmetic anymore. It's going to be square roots and everything else, because so many things are really in complex form, complex number form, reflection coefficients, all of those things. So you just have to really learn it. So what I like to do is, I'm probably going to hit a key here by putting this over here, but I'm going to try it. Probably not a good idea. What I like to do, well, here's what I could do. I could push that, yeah, no one's looking at me. I can push that back a little bit, and there you go. That's better. Now, we really already know time domain form, right? So we've got time domain form, which would be something like V of t equals V maximum, and by the maximum I mean the peak voltage, times the sine of omega t plus phi, right? Something like that, time domain form. And then you guys have learned phasor form, where it's really just the maximum, and then we're just really looking at the angle, right? Plus, we know, and that's if really we're basing this on sine, right? If everybody is on top of the, I mean, usually cosine would be the thing that would be there, I would think, although you guys may, as you've come through your education, learned that sine is really the thing that you've got with phi. Anyway, it doesn't matter right now. So what we would look at then is V max times the cosine of phi plus j V max times the sine of phi, right? And that would be your A plus JB form of the complex form. So anyway, you've got three forms there, right, that you see. So what we want to look at is what is the e to the j theta, and how does a e to the j theta, which is the exponential form of all of this. All of this is all related, and this is, a lot of times you'll see in this is the power, so this is like divided by the square root of 2, so it's the RMS voltage. Some people say that, some people don't, but really when you get to the e to the j theta, how do we know that? And what I want to point out to you is this truth, right? E to the j pi plus 1 equals 0. Right? That's what we want to look at today. So you know, when we just look at the expansion series for e to the x, we see that the expansion series is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus blah, 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 blah. We can keep going on. And really what I want to do is I want to go on to 7 factorial. So let's do that. By then you'll get the whole idea of everything that I'm really doing. Now, we also have cosine x. And the expansion series for cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Maybe I can use this other pen, might be a thinner, finer thing here. Okay, and then plus blah, blah, blah. Yeah, it looks a bit thinner. And then sine x, if I look at its expansion series, it is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I think everybody can probably see where I'm going with this. Minus x to the 7th over 7 factorial, right? So I think that everybody can see e of x, cosine x, sine x that we have right there. So what I want to do is I want to look at the expansion series of, and I'm just going to hopefully I can just sort of drop a line down here, and those couple dots aren't going to worry us too much. And what I want to do is I want to use this side of the paper over here. And I want to look at the expansion for then e to the j theta. E to the j theta. Let's go over here. So we start off with 1, don't we? And then the second thing we start off is, the second thing is plus j theta. Right? Does everyone see that? I'm just taking j theta, which is the argument to Euler's constant here, right? To the exponent of Euler's constant. I'm taking j theta, just like I'm doing here for the expansion equation for e to the x. So I've got 1 plus x, and x would be whatever the exponent is on Euler's constant, and that's j theta. So I've got j theta there. Now let's go to the next thing. Plus x squared, right? So that would be j squared theta squared, right? Over 2 factorial. Let's go to the next one then. Plus, now I've got j cubed theta cubed over 3 factorial plus j to the 4th power theta to the 4th power over 4 factorial plus j to the 5th power theta to the 5th power over 5 factorial. And I think I've just run out of room there, but I think that you get the general idea. And so that's what I want to look at here is, you know, e to the j theta. Now, what I want to do is I want to simplify that a little bit, right? I think that everybody can see. I'm going to just have a sip of tea here. No, I'm probably going to spill this whole cup. I made a whole cup of hot tea. I haven't taken a sip yet. I don't have the timer on. I have no idea how long we've been working here. But I'm thinking it's been about maybe 5 minutes. I'll tell you what, just for safety's sake, I will dial this back 5 minutes, 6 minutes, and start it. There you go. I found that Zoom is a much better video compressor with the new updated version they just put out. So, okay, so e to the j theta. Now what I want to do is I want to break that up a little bit. Now, I've got 1. Let's just look at that first. In fact, where I wish I had my red pen. Where the hell did that red pen go? No idea. Okay, well, I'm going to have to go with the blue pen then. So let's look at what I've got here, because I'm going to break these up into 2 different groups. All right, so the first one is 1. And then let's look at this guy, right? Yeah, I could, no, let's just do it this way. So 1, and then let's look at j squared theta squared over 2 factorial. What's j squared? Isn't the definition of j that it's the square root of -1? Well, the square root of -1 squared has got to be -1, right? So this would be 1 minus theta squared over 2 factorial, right? Let's look at this one over here. Now I've got j squared theta to the 4th. J squared, well, j to the 4th, theta to the 4th, and j to the 4th is really j squared times j squared, isn't it? And j squared is -1, so -1 times -1 gives me +1. So this would be plus theta to the 4th over 4 factorial. And we could just imply, what's going on from there. Now, let's go to the next box that I have here. So plus. And now what I want to do is I want to pull everything that's inside that box. I'm going to pull a j out of it. And so the first thing that we come across, and what I want to do first is I want to circle the components of this equation over here in blue. I hope everybody can see that in blue. It's blue. It looks almost black on my screen. So those 3 things are what are incorporated in that first bracket, right? And now I'm pulling the j out of there, and as you can see, the first thing that's wide open again is going to be theta, right? And then let's look at this one. Well, plus j cubed. Well, if I took a j out of there, that would leave j squared, wouldn't it? J squared is -1 theta cubed over 3 factorial. And then let's go to the next one over here. Well, if I took a j out of there, that would leave j to the 4th power. And that's j squared times j squared, and -1 times -1 is 1, plus 1. So this is going to be plus theta to the 5th power over 5 factorial, right? Does everyone see where that is going? So e to the j theta is just going to be, and this is what I wanted to prove here with this. When we look at the expansion series, well, let's look at this one. 1 theta squared over 2 factorial, 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. Well, that's cosine, isn't it? And it's cosine of what? Cosine of x or cosine of theta. So cosine of theta, right? Plus j, that's why I took the j out of there. And then what's inside this box? Well, I've got theta, sine of x, theta, minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. Do you see how it lines up? So this, of course, is sine theta. So e to the j theta is cosine theta plus j sine theta. So I just wanted to point that out. And of course, if you look at what I wrote up there, Feynman's lecture, e to the j theta, well, what would that be? E to the j theta then would be cosine, or e to the j pi would be cosine of pi, cosine pi, plus j sine pi plus 1, right? That's where the plus 1 comes in. Well, let's see. Cosine of pi is minus 1, right? Plus sine, j sine of pi, well, sine of pi is 0. So minus 1 plus 1 equals 0. Does everyone see how that all works out? Of course you do. I'm sure that because this is probably saying, oh God, I don't even have to watch this because this is just such a review for me. That's what I hope you're saying. Now, after doing that little review on e to the j theta, what I always like to do is say, well, okay, well, if that's e to the j theta, and of course, if we just put a in front of it, it's yeah, that's just a multiplier, right? So that has nothing to do with anything. So what's e to the minus j theta? And I think everybody can see from what we have here is that that is just going to be cosine of minus theta plus j times the sine of minus theta, right? But what is the cosine of minus theta? The cosine of minus theta is theta. And if you don't know this, I'm going to refer you to the unit circle here. I'm just going to draw the unit circle. If you can't imagine it in your head, there's the unit circle. And if I have the cosine of something, let's say that I'm looking at that angle right there, well, obviously this would be the cosine. And if it was a negative angle, it would be the cosine too. So I'm just saying that the cosine of negative theta equals the cosine of theta, right? I shouldn't even have put those brackets around there, but I did. Now, how about the sine? Well, if we look at the sine of theta and the sine of minus theta, they're opposites. So the sine of minus theta, doing it again, equals minus the sine of theta. This is my third lecture today. No wonder my throat's giving out. Warm tea. Now, so what we could say here is that this is the same, e to the minus j theta is the same as the cosine of theta, right? Minus j times the sine of theta, right? And so keep that, always remember how to do it, is what I say, but just remember that. So e to the j theta is cosine theta plus j sine theta, and e to the minus j theta, of course, just changes that, and it's a minus instead, and I just explained why that is. And so that, the reason that I point out that the exponential form is so important to you is because that's all you're going to use in the future. Congratulations, here's your magic electrical engineering handshake. All those time domain and phasor things and everything else that you've used. Oh, that was so fun, wasn't it? But yeah, e to the j whatever is what you're going to be using. Now, when we talk about complex numbers too, I just want to talk about a couple things. Complex conjugates. Now, let's say that I was representing a complex thing. Let's say current, right? And it was A plus JB. then the complex conjugate of the current, which is usually denoted by an asterisk above it, the complex conjugate of the current would be A minus JB, right? If I was to multiply a variable times its complex conjugate, right? Let's say that I've got A plus JB times A minus JB. Well, wouldn't that give me A squared? And then it would give me A times or minus JAB. But hey, then the next one I get plus JAB, so they cancel each other out. And then what I get is I would get minus J squared B squared, right? Minus J squared. Well, J squared is minus 1. Well, a minus of a minus is a plus, so that's B squared. If you were freshmen, I'd do that for you, but since you're seniors, I'm assuming you've already had this, and this is just something that you understand necessarily. Another thing that I like to point out to everybody to homogenize the class, even at the senior level, if at all possible, is division of complex numbers. So when we're thinking about division of complex numbers in their, A plus JB form, you have, I'll give you one. Let's say that 3 plus J4 is divided by 2 minus J3. Now, how many people know how to do that? All of you do. I see you're all raising your hands. That's so good. So I don't even really have to do this. But really, what you do is you take 3 plus J4, right, divided by 2 minus J3, which is what you've got there. Multiply it by 1. But that 1 is the complex conjugate of the denominator, right? So that's what I'm going to do. I'm going to multiply it by 1, but it's going to be the complex conjugate of the denominator. So when I multiply through here, 3 times 2, right? That gives me, wait a second, what have we got there? Well, actually, I can just give you the answer. Minus 6 plus J17, right? And then when I look at the denominator, I just have to have 2 squared, that's 4, and 3 squared, that's 9. 9 and 4 is 13, which is a whole number. So I can just divide that out, and that gives me 0.046 plus J 1.31. Does everyone see how that was done? How I divided? I had 2 numbers in this complex form, and then I could just work through that. And I'm sure that, like I say, your math department is just focused like a laser beam on teaching you what you're going to need in electromagnetic field theory too. Oh wait, no, this is just electromagnetic field theory. Yeah. Sorry. Anyway, so that basically sort of takes us through, some stuff with complex numbers and everything else. I just wanted to do sort of an example down here. Let's say that I had 5e to the j 0.295 pi. And I was multiplying that by 3.61 e to the minus j 0.313 pi, what would I get? And I think everybody can see. First, you multiply the magnitude, 5 times 3.61, and that gives you 18.05. And then with the E, just like you do with phasors, you just add the two angles together here. You've got 0.295 times pi and 0.313 times pi, negative 0.313. So it comes out to minus 0.018 pi. So do you see it works just the same way as phasor notation really would work? And of course, it does. And I just wanted to point out the other stuff. I want to go through an example problem, which I think I'm going to have to do in the next class, because I have no paper left. So I hope everybody enjoyed that exponential form. There's going to be one more on that. I'm just going to work through some stuff so that I make sure that you all know it and have seen it. And so if you ever go to grad school and start, working in electromagnetic field theory or into actually a lot of careers out there using a lot of electromagnetic field theory too now. Yep, it's a wonder where the human race is still living. All right, on to the next lecture.